Now, so now we forgot to record, so here we go, quickly. So I want that to be on the document camera, on the video. Revisit that quickly, so I'll fly through it. We were talking about units we use in circuits, and just like in physics, the meters measure the distance in meter, mass in kilogram, time in seconds, current in amperes. In a few minutes, you're going to hear me talk about voltage. Voltage is measured in volts. Power is measured in watts. Resistors measured in ohms. So we have special units we use here. We also use the pico, which is 10 to the minus 12, nano 10 to the minus 9, micro 10 to the minus 6, milli 10 to the minus 3. These are common ones we use. For more than one or more than 100, the kilo is 1,000, mega is a million, giga is a billion, and tera is a trillion. And we use capital letters for anything over 1, smaller letter for anything below 1. And we define a charge by counting how many, the total charges that went through a cross section. Again, if you're watching, counting how many charges going by that little piece there in 1 second, and you add all these charges, that's what the charge is called, coulomb there. And again, we measure the charge in coulomb. So the example I was doing here, I said if I have a wire and this is a window here, I'm watching it through this window, I'll make the window a different color, like red color. This is a glass window, and I'm counting how many charges going through that window. In this example, I said, let's assume 1 million electron went through it. Then the charge will be, each electron has a charge of negative 1.6 times 10 to the minus 19 times the million of them, and that's what the total charge is. In this example, I was watching through this window and counting how many protons are going by. And I said, let's assume that we have 24 million proton actually went by in 1 second. The charge will be, this is the charge of one proton, this is the number of them, you multiply them, and that's what the total charge is. So now we're back on track. Current. Now, current is defined, we use the letter I, by the way, for it. Amperes, which we use the letter A for current. So we said this fuse on the circuit breaker is 25 amp fuse, or this fuse is 20 amp fuse, or this circuit breaker will trip once you exceed 15 amps. That's the maximum on these. If you go to your parents' basement and you look at your circuit breaker, and you have these switches here. If you have a 200 amp circuit breaker there or board there, you have two sides, usually. If it's a 100 amp, it's smaller panel with one side. So this might say 15 amps. This might say 20 amps, 20 amps, 25 amps, 30 amps. What does that mean? Usually when you see like something like 30 amps, that's probably going to the kitchen. Because in the kitchen you have a lot of appliances. You got the dishwasher, you got the microwave, you got electric oven possibly, a fridge, garbage disposal, toaster. When you put all these on, sometimes you have I have the dishwasher running, I have the microwave going, I'm making coffee at the same time, I'm making my breakfast, I have the stove going. I want to make sure I have enough current going to all these appliances. This 30 amps says all these currents combined cannot exceed 30 amps. Once they go over 30 amps, it will trip the circuit breaker. That's the purpose of that. Now, I've seen people going, oh, the circuit breaker keeps tripping. Let me put a bigger one. Let me put they have a 15 amp. Let me put a 30 amp here. So now instead of 15, it's 30. Wonderful. What's the drawback to that?
Wires are...
Exactly, the wires. The wires was attached to the 15 amp, not a heavy duty wires. They can handle up to 15 amps. Now you try to get 30 amps out of them, they're going to get hot, they're going to overheat, and you're going to have a fire in your house. That plastic is going to melt on them. There's different gauges. There's a maximum to each one. So when the electrician comes into your house and rewire your house, they have to know, or they have to put the right value there. You know. So we measure current in amps or amperes. Now, current is defined mathematically as the change, dq, this is calculus now, dt, the derivative of the charge, the change in charge per time. Now, if we play with the math here, if we cross multiply both sides by dt, the equation, we have dq equals I dt. And if we integrate both sides, what's the integral of dq? Q. What is the integral of I dt? Well, this is really, we're not sure what I is, but it's the integral from 0, or negative infinity, not 0, to t, I dt, right? I can break the integral down to two things. I can say integration, I go from negative infinity to 0, I dt, plus from 0 to where? To ti sub dt. Well, this equivalent to what? The initial charges. So q, the charge, is really the integral from 0 to t, I dt, plus the initial q at 0. The initial charge that was there. Q at t0, if you don't want to say 0, t0, initial time. So if you don't want to use, because nobody knows what 0 time is, so you might want to call it t0, you know? t0 is the time you go to the lab when you connect this. So if you don't want to use 0 time, because there's no such thing as 0 time, what is 0? Does not mean midnight, you know? To me, 0 time is when I go and build the circuit. That's 0 time. So we can make it t0 here, if you want it more general form there. So the current, again, two equation. This is one. The current is the derivative of the charge, or the charge is the integral of the current plus the initial charge. We do a little bit of calculus here in this class. That's why to take this class we ask you to make sure you finish Calc 1, and you in Calc 2 you do an integration. Hopefully you're done with Calc 2, because that's integration there. Current could be positive, current could be negative. Let's talk about current, because that's what I'm really focusing on. What is a positive current? What is a negative current? Let's say we have a wire. Let's take this example. Again, I'm still talking about current here. And let's say we have a wire. And in this wire, I notice the current going left to right. I equals 5 amps. If I ask you, can you tell me what this current is equal to? What do you think? Negative 5 amps, exactly. So you'll see me use positive and negative current. Is nothing more than changing the direction, you know? A lot of times when we do a current source, we draw the picture for a current source. Let me see if our book, no, the book doesn't, but I'll talk about it. When I draw a current source, I have a current source, I draw something like this. I have a current source, I use an arrow, of 3 amps. Or I might say I have this current source pointing down of negative 4 amps. When I see one that's negative, I don't really like negative numbers. I take this current source, I say I'm going to change it to a positive. And the way to change it to a positive, what do? Change the direction of it. I switch the direction, and make it 4 amps. Remember, current is like water. Now, what do I mean by current is like water? If you have a hose, just think of water. If you have a hose and you attach a smaller one to that hose, a smaller one, and let's say we have 2 gallons of water per minute going through this big section. How many gallons of water going through the little section per minute here if there is no leak in that hose?
Same.
It better be 2 gallons per minute. So with current, if I have a current source, that's a current source here, of 3 amps pushing up, and I attach another current source in this direction of 4 amps, that can't exist. That's impossible. Why? Just like having that picture. Notice the current going up. I just bend the wire, big deal. If I don't bend the wire, I'm saying that 3 amps going this way. Going through this, pretend that's a hose, going through that hose. And now we got 4 amps going through that hose. How can you have 4 amps and 3 amps going through the same hose? You can't. So that's definitely wrong. Definitely. Now, think of water again. Can you actually take a hose that does 2 gallons per minute of water here, and couple it, let's say we buy this like 2 to 1, attach it here to this attach it to this now, and this one has here another hose that pushes 3 gallons gallons per minute of water. How many gallons of water coming out of this end then? 5 gallons per minute. Since current is like water, if I have a current source going like this, pushing 3 amps, I have another one joining it, it's not a 4 amps pushing that way, and I said to you, now what is this current coming out of this end? That should be 3 plus 4, which is what? 7 amps. And the marker died, the good marker just died. Where current is different than water, I'll show you where. If you have a hose, again 3 gallons per minute, and you take and you cut it with the knife here, what happens to that water? It shoots out, right? Some might even make through the other end there. But you take a wire now, 2 amps going through it, and you cut it, how much current going through that? 0. That's the difference between them. It doesn't jump. So once you have a hole in the circuit, there's no current going through it. So when I have a 3 amp source like this one, and I take a 2 amp, and I connect this end, and I forget to connect that end. It's not attached to it. It's close to, but I don't have enough wire to reach there. And I say, what's the current going through this now? 3 amps. Because there's a hole here. This is not attached to that. It doesn't just jump. So that's how current is. Next topic is voltage. voltage here. Where'd you go? Where'd I put you? There we go. Hopefully this is still working. The battery is good in it. This is actually a meter that I can measure the voltage and the current. If it's still charged, we'll know in a second. Oh, I hear some noise. Oh. Come on. Something loose there. I have to get new batteries for this. It's like you gotta twist it. Okay. Oh, maybe the switch is broke. Let me see. It should. If I touch this, should be 0. There we go. Ah. Come on. Yeah, it's still in the drawer for a while, so a cheap one. Maybe I'll get a different one day. Yep, stay there, stay, don't move. There we go, 0 voltage. Now there's a new set of batteries. These are AAA battery. What's the voltage on a AAA battery? 1.5, so it should be close to 1.5.
Low battery.
Come on. If I hold it with 2 hands. I gotta get a newer one, I guess. But that gives me actually here, if I can get this to work, I know it needs a battery. I'll throw it in the trash later. But if I take a battery that's 1.5 volts, that means when you look at the battery, with the way we draw that by the voltage, we measure the voltage in volts. We go 1.5 volts. Well, you're not going to write the word volts, so we write that 1.5 V for volts. And the way we draw, especially a DC, a battery like this, a DC, we have 2 wires. Sometimes I use 4. The longer one is always the positive. The shorter one is always the negative. That's the standard. So this is a 1.5 volts. Sometimes I draw them like this, 2 of them. And I go, that's still a 1.5 volts. The fact the long wire on the top, that tells me that's the plus. The short wire on the bottom, that's the minus. In some case, we draw the voltage source, circle, plus minus. We go, that is 1.5 volts. We usually use this for a battery, and we use this for a source. That's not a battery, you know. Like when you're in the lab and you turn the knob, we use that picture, but it doesn't really matter. Everyone knows that means voltage here. Now, where voltage is different than current, again, with current, we said this is not good. If you take 3 amps, attach to it 2 amps here, not good. Can't be. This is not good. With voltage, if you take 1.5 volts and attach to it another 1.5 volts on top of it, guess what the difference between the top and the bottom now? It's going to be 3.0 volts. So this is good. I'm doing current versus voltages here. I'll make a chart like this. The other thing with current, we said if I have a 3 amp here, a 2 amp here, you attach them together, what's the result coming out of this? 5 amps. In voltages, if you take a 12 volts here and you attach in parallel to 3 volts, that's not good. Why? They're supposed to be the same voltage. We'll get to that. That's called parallel connections. When things connected in parallel, they must have the same voltage. How can these two have the same voltage if one of them is 3, one of them is 12? So guess what will happen? Either the 3 will try to drain the 12, or the 12 will try to increase the 3 to 12, or to 11 or 9. What happens when your car dies, the battery dies outside? You jump start your car, what do? You find somebody with a good battery, you attach the plus to the plus, and the minus to the body or the minus. And what happens, you force that battery to go from 3 volts now, because they're connected in parallel, try to match the 12, and your car will start. You do that 5-6 times in one day, your car, the good car, will die. Because you can't have this. So they're going to find a common ground. Okay, can't be 12, can't be 3. What can it be? Maybe 11. If you let it stay connected for a while, this will start to lose its value. Do it again, 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 and again, 5-6 times. Each time you lose a little bit. By the end of the week, this car won't start. This is called parallel connection down here on the bottom. And in parallel, we know they have the same voltage. And the top connection is called what? Series, yep. These have what? Same current, not voltage. That's why this is a no-no. You can't have 3 and 2. It's supposed to be the same current. They can be 2 and 2, but not 3 and 2. These can be 12 and 12. That's okay, but not 12 and 3. When we draw a picture like this for a voltage source, what that means, I'll wait. When I draw a voltage source like this, and I got 2.5 volts, what does that mean about the voltage here on the top? If I draw them the way it is. Let's say this is the top, and this is the bottom. What does that mean? You said positive what?
Positive 2.5 volts on the top.
Maybe. Jordan. Jordan says positive 2.5 on the top. I says maybe. And maybe not. Depends on what?
Direction.
Well, the direction, the plus is the top. The bigger one is the plus. The smaller one is the minus.
Or whatever, the way the current's flowing.
No. Current will not determine what the voltage there. What that means, the voltage at top is going to be the voltage at bottom plus 2.5. That's what that means. This end is 2.5 higher than this end. So Jordan is kind of right when he said the top is 2.5. If this is 0 voltage. If you attach this to the ground and this is 2.5 volts, Jordan is right. The voltage at the top is equal 2.5 higher than the bottom one, which is what? positive 2.5. And when I said to Jordan, maybe you're right, maybe not. But what about the bottom is negative 5 volts here? And what's the voltage at the top here? V at the top, and again, this is 2.5. This end is going to be 2.5 higher than that end. It's going to be 2.5 plus the negative 5. And what's the voltage on the top? Negative 2.5. So all that means this voltage is 2.5 more than this. And it depends where I've attached to this one. If I make this negative 2.5, this is the top here. The voltage at the top is going to be what? 0. It's 2.5 higher than this, 2.5 more than this. So whatever this voltage is, add to it 2.5, and that'll give me a 0. But a lot of people will think, they see a 2.5, they think the voltage at the top is 2.5. That's only correct if this is 0 or ground. When you attach it to the ground, when you build a circuit in the lab, you'll see that we always have one ground. So if I give you this circuit here, pretend we have this circuit. I have a current source, since we cover current sources, of 6 amps. I have a voltage source here of 4 volts. I have a voltage source here of 2 volts. I have a voltage source backward here of 5 volts. I have a current source here of 2 amps. Given that circuit, and let's say I take this and I attach it to ground. That's my ground. Ground means what's the voltage? 0 volts. So right here is 0 volts. Can you tell me what the voltage at point A, what the voltage at B, what the voltage at C is? What is the voltage at A? It's going to be 2 volts higher than this. What was that? Is that my machine?
Yeah. Voltage meter. It's the multimeter.
Is it? Oh, it's hunted. What is the voltage at B? It says this end is going to be 4 volts higher than this. So this here is 2. 2 plus the 4, which is what? 6 volts. What's the voltage here, by the way? A, B, C, D, E. What's the voltage at D? Voltage. Why 6? This is 0 right here. What is it here? Let me ask you another question. How is this set, this group here, connected in relation to this? Parallel. And if they're in parallel, where's my note? They must have the same what? Parallel have the same voltage. So this end and this end should be the same voltage. So you were right when you said 6 volts here. What is the voltage at E? 6. This is a whole group in parallel with this, in parallel with this. 6 volts. Now, what's the voltage at C? Remember, this is 6 right here. So what do you think C is? 11. Why? The way it's labeled, it says this end, that's the plus, this end is going to be 5 more than this. See the minus plus? This end is lower, this end is higher. This end is going to be 5 volts higher than this. So that will be the 6 plus the 5, which is 11 volts. Yes?
Voltage would be, how do you get 6 volts again?
This whole thing is in parallel with this.
No, for B, voltage B.
Well, this is 2 here, right?
2,
Because that's 2 more than this.
wouldn't it be 0 though?
This is 0 here.
Yeah, it's 0.
This one is going to be plus minus. That's 2 volts higher than this one.
Mm-hmm.
So 2 higher than 0, which is what?
Which is 2.
2. This end is going to be 4 higher than this end.
Oh, okay, I see it. Okay.
Yep. Okay. So that's voltage here. Next topic is power. P is power. Power is defined as the voltage times the current. V times I. And what is the unit for voltage? Volts, right? What's the unit for current? Amps. So it's VA. But instead of saying VA, James Prescott Watt did a lot of work on power, so we decided to call the unit watts. So it says this is 15 watt light bulb. This is 75 watt light bulb. So we use W for watts. Now, power can be positive and power can be negative. If it's positive, it means it's absorbed. If it's negative, it means it's being supplied. And how do we know if it's positive versus negative? Here is the scenario for that. When the current arrow is directed into the element at the plus marked terminal, we satisfy the positive sign convention. In other words, it says that if the current arrow, the direction of the current, and the voltage polarity, that's the plus minus sign, are placed such that the current enters the end of the element marked with the positive sign, then the power is absorbed by the element. Otherwise, the power is being supplied. What does that mean? If I have an element, this is the element, and this is the plus, and this is the minus. And I have the current. The current is traveling this direction of 3 amps. I have the arrow of the current, the direction entering the plus. See it? Let's say this is plus 4 volts here. Then the power by this, I don't tell you at absorb or supply. If we have a current entering the plus, let me read that again to you. In other words, we say if the current arrow and the voltage polarity signs are placed such that the current enters the end of the element marked with the plus sign. Is that what we have? Is the current entering the plus sign? Yes. Then the power absorbed by the element. So that's a positive power. Positive means absorbed here. And the value of the power is voltage times current. What is my voltage here? 4. What's my current? 3. That's 12 watts absorbed. On the other hand, if I have this picture, and I have the current entering this. So notice the current does not enter the positive, enters the negative end. Then the power here will be negative V times I. Negative 4 times 3, which is negative 12 watts. The negative indicates the power is being supplied. So positive power means absorbed, negative power supplied. The resistor normally takes the power, absorbs the power. The source most of the time supplies the power. You just have to be aware, sometimes we play a trick at you, we give you negative current. So I'll have this element here, plus to minus 4 volts. And I say I have a current going this direction, I equals 3 amps. Or negative, not positive. Negative 3 amps. Up. Negative 3 amps. Well, then negative 3 amps, it means what? When you look at that circuit, well, it means what? The current wasn't really going that direction. Which way? Because negative current, it's 3 amps coming out of this. That's what that means. And if it's coming out of this end, then which end was it entering?
The negative.
The negative end. It looks like a 4, but I keep doing it, but it's a plus. That means really the current was entering that end, the 3 amps. That's why it's coming out of that end. There's only one way to enter, one way to exit. If it's coming out this way, it was going out through that end. Now notice we have the current entering the negative end. The power becomes what? Negative. Negative. 3 times 4, which is negative 12 watts. Again, the negative means supplied. Again, we could reverse them. I'll do one more example. Let me reverse them. Let me reverse these. That's all right. Leave it. Let's have negative 4 volts here. Negative 4. I equals negative 3 amps. Notice this negative 4 volts, and that's negative 3 amps. We know what the negative 3 amps, we just did that right in this example. So that negative 3 amps really means the current was going in this direction of 3 amps. But what about the negative 4 volts? That means what? You can switch the polarity, exactly. You can switch that, make that a minus, make that a plus, and that's 4 volts instead of negative 4 volts. Now you have what? A positive current entering what? The plus. So is that positive or negative? Positive. 3 times 4, which is positive 12 watts. Again, the plus indicate the power was absorbed. So the key to that statement has to be a positive current, not a negative current, entering the positive terminal of a voltage source. And again, be careful. That looks like, you know, when this is -4, you got to flip them, take care of them, make them change the direction of them. So first you got to get rid of all the minus sign, make them all positive, all the negative voltage, and take a look. Do you have the current entering the plus or the minus? If it enters the plus, it's a plus. If it enters the minus, it's a minus. Minus means supplied, positive means absorbed. Okay, you try it. Tell them, calculate the power. Give it a try. This is what I have. I have an element here. I know this end is positive. This is negative. 220 millivolts. And I know the current coming down is 4 amps. What is the power for this one? And tell me plus, minus. The other example, I'll give you 3 of them. If you finish with that, I'll throw the other one, then we'll come back. This is the element. I'm not telling you what's in the element. I got plus, minus, and the voltage here negative 3.8 volts. Plus, minus, plus there. And I got a current entering in this direction, I of negative 1.75 amps. What's the power of this one? And the last one, I go negative, positive voltage here. Eight e to the negative 100 t, that's the voltage. It's not just a DC value. And the current is going this direction of 3.2 amps. Maybe this one will be specific. What's the power at 5 milliseconds? Otherwise, your function is going to be a function of time. Now, the first one, if you look at it, the current's coming down. That means, where's it coming from? It's coming from the top. It's entering this way, right? So we have 4 amps. We didn't change the direction of it. 4 amps entering which end?
Positive.
Plus, that's a positive 4 times the voltage is 220 milli. And you end up with what? 880 milliwatts. Positive.
So it's okay to keep it, those units, milliwatts?
Yep, milliwatts.
So that'd be 0.88.
You can write 0.88 watts if you want to, yep. Or 880 milliwatts, yep. This one I got to redo. I don't like the minus plus the way I have them. So really what that means to me, since this is a negative voltage, it's actually plus here, minus here. And what's the value? 3.8 volts. Right? Since my current is negative, is going that direction, that means it's what? It's going this direction. What's the value?
Negative.
I mean 1.75.
Oh,
The current, right?
right.
So now the power, we have a positive current entering which end of the element? Negative, that's a negative power. 3.8 times 1.75. That's a negative 6.65.
Wait, how does it be, how is it negative? Because that enters the negative side?
Well, this is
So another.
a negative, and that's a negative plus. So because that's a negative, it's going to switch the polarity. It's going to make this positive if you change the direction of them. And this current is negative, is going to be positive in that direction.
If you just write supplied in 6.6.
You could.
5 watts, is that fine?
So, yep, you can. Our book uses plus minus for that example. You know. So this one, this is a positive. Remember, 8E. E will never be below 1 here. Or below 0. Could be below 1, but not below 0. E to the minus. If you remember the graph exponential functions, they go through an exponential function has a graph that looks like this. Any exponential function. This is a negative exponential. The graph will look like this. Right? This is the 1, 0. Or 0, 1, not 1, 0. So that's the graph of E to the negative 100t. Notice the value is always what? Positive. You multiply it by 8, still positive. So this is a positive value. I don't have to switch it. Minus here, plus there. We have the current entering which end? Negative. So the power as a function of time will be negative, because you have the plus current entering this end, 3.2 times 8e to the minus 100t. Negative, what's 3.2 times 8? 25.6 e to the negative 100t. Now we want it at what time? 5 millisecond. That'll be negative 25.6 e to the negative, is that 0.5? 5 millisecond. When you take the t and replace it with 5 times 10 to the minus 3. Huh? Yep. So 25.6 e to the negative 0.5. Let's see what that number is. E to the negative 0.5. 15.52. Negative 15.53 watts. So at that time, that's how much power is being supplied, because that's a negative, supplied by the source. Okay, that's the first part.